This is a video tutorial to study a discrete time simulation, and specifically looking at the delay system example. When I talked about this system in lecture, I described it using a transition and output table. This has a number of columns which provide the following information. It describes what the current input is, x of t, the current state, q of t, and based on these two pieces of information, it can describe the next state, q of t plus 1, and the current output, y of t. So this tabular format gives a very concise notation for all the different possible combinations of inputs and states that yield different sets of next states and outputs. So for example, if we have 0 initial input and 0 state, so that would look something like this. We have 0 being input to a cell or a stateful machine with current state 0. Then you could describe or define, for example, that the next state is also 0 and the current output is 0. So what this would yield is in the next time step a state of 0 and a current output of 0. So this is at time t, it's at time t plus 1. So we can start thinking through some of the other combinations. So in this case, there's really 4 different combinations. We can have input 1, state of 0, input 0, state of 1, and finally the last case is input 1, current state 1. Right. So for the delay system, the transition and output table describes specifically what the next state and output are in these different cases. So specifically it defines the next state to be 1 and that current output to be 1 in this case. And again, that means that if at a current time we have state 0 with an input of 1, then the current output should be 1, and at the next time step, the state should switch to 1. In this next case, if we have input of 0 and a current state of 1, the delay system defines that our next state is 0, the current output is 0. So again, if we have an input of 0 and our current state is 1, our current output should be 0 and our next state should be 0. And finally, in the last case, if we have 1 input and 1 current state, then our next state is 1 and our current output is 1. Right, so again, we have the input of 1, current state is 1, our current output should be 1, and our next state should be 1. Another way of representing this table is to actually define functions for these two columns. So the next state column in this table we've described as the state transition function, or delta. And in a general system, the delta function can be a function of the current state q and the current input x. In this particular case, it's clear that the next state is just equal to the current input. In this case, the delta function is simply equal to x. Similarly, we can define an output function. In class, we've used the notation lambda, and similar to delta, it can be either a function of q or x, or both. And in this case, we can see that the output always matches the input, right? In each of these 4 cases, the output is exactly the input. So in this particular case, another way of representing this column is lambda of q and x is equal to x. Now, given this definition for a delay system, then we can think about different cases of input trajectories. So the example that I gave in lecture was if we have a particular input trajectory for time steps 0, 1, 2, and so on, we can give an alternating input between 0 and 1. So this is the input x of t versus t. So we could say, for example, at time 0, the current input is 1, then it turns off, no input at time step 1, then it turns back on at state 2, or time 2, then off time 3, back on at time 4, off at time 5, and back on at time 6. Now, using this information, we can also then figure out what the state trajectory is. Right? So the state is q of t over t. We have the same time steps, 0, 1, 2, 3, 4, 5, and 6. We have to be given what our initial state is, so whether it's either 0 or 1. So let's just say, for example, that in this case, the initial state is 0. So q at time 0 is 0. This has to be given because there's no other way of figuring out what our first state will be. Now, if we can use our transition output table or our next state functions, we can determine the successive state at each time step. So we can look, for example, if we have an input 1 and a state of 0, we can look up in the table, input of 1, state of 0, we know that our next state is 1, right? So at time 1, our state is going to flip over to be 1, following directly this state, this transition table. Now at time 1, we can look, we have 0 input and 1 state. So 0 input, 1 state. Our next state is 0, right? So we can add in, we can define what our state is at time 2 based on the information that we have at time 1. And we can continue following this process. Again, input is 1, state is 0, our next state is 1. And in this particular case, because the next state keeps following the input at the previous time step, right? So q of t plus 1 is delta qx, in this case is x. This state is just going to be alternating between 0 and 1 to exactly match our input. Now the last little piece of this problem is to figure out what the value of the outputs are over time. So we have the same time steps, 0, 1, 2, 3, 4, 5, and 6. And our output is y of t. It also is either 0 or 1. In this case, again, we can use our current inputs and our current states to figure out what our current output is. So if we have 1 input and 0 state, our current output is 1. Right? So just exactly following our table. Similarly, if our current input is 0 and our current state is 1, look it up in the table, input is 0, state is 1, output is 0. Right? Because again, our output function, y of t, is equal to this lambda function of possibly q and x, and in this case, it's only it's only x. Right? This is the functional form that we've identified. Our output is going to identically match our input in this case. So at each time step, the output will be a mirror copy of our input.